We're going to go ahead and go through the notes for section 1.1, subsets of real numbers. So our objective for today is that we're going to understand the real number system, and we're also going to understand its subsets. So all the numbers that we use, any number that you can think of is a real number. Any number that you've ever used in the past, anything that we're going to use this year in this class is a real number. So the real number system, so the whole system that has all of these numbers that we've ever used has multiple subsets of numbers that we can use to classify these numbers. So we have multiple subsets, and we use these subsets, which I will define a little bit more in just a moment, to classify numbers. So we'll be able to explain and group up numbers in different ways. So these subsets are rational and irrational, we have integers, we have whole numbers, and we have natural or counting numbers. This last one has two different names. So we can call it natural numbers, or we can call them counting numbers. So let's think a little bit more about this real number system and what numbers I am talking about. So if we picture a number line, it goes on forever. So I can start at 0 on the number line, and I can go forever to the left to go negative. There's always a more negative number. And then I can go forever to the right, so I can always get more and more positive. So every point on this number line is a real number. So while we're picturing this real number system or this number line, you don't need to draw this, but I'm going to go ahead and draw this number line down here. Those arrows show that no matter which direction I go, it goes on forever. So say I have the point 0 right here. And then right here I have the point 1. Well, there's no gaps. Even when we're looking at this area in here, between 0 and 1, there's no gaps. Because I can point to that spot right there and say, oh, I think that's 0.5. I can point to that and say, oh, that's probably 0.25. So every single spot on this line has some kind of number assigned to it. So between those whole numbers that I showed, that would be like 0 and 1, and all those fractions, or those decimals that I just showed, I showed 0.5, which is the same as 1/2. I showed 0.25, which is the same as 1/4. Between all of those numbers that we're used to, there are numbers that are irrational. So this means that they're decimals, but they don't terminate, which means they don't end, and they're not recurring, which means that they are not repeating decimals. So these decimals go on forever and ever and ever. All right, so when I'm talking about sets and subsets, just so you kind of have a little bit more information about this, a set is any group of distinct, so different numbers or objects. That is what a set is in math. And then a subset is a group of distinct numbers or objects within that set. So what we're going to be talking about is the real number system as a set. So this set is every possible number you could ever think of. And then the subsets are going to be different types of numbers within this. Another example is I could have a set, which is typically written in math with these little fancy curly brackets of 0, 1, 2, 3. So say that's my set. then my subset would be something within that. So maybe my subset is the list of positive numbers within that set. So my subset would be 0, 2. So even though there's more positive numbers out in the world, within this set right here, my only positive numbers are 0 and 2. So that makes that my subset. All right, let's go ahead and talk about these subsets a little bit more. So we're going to start with our smallest one. We're going to start with the counting or natural numbers. So this is the set of numbers that we use to count. So within our whole real number system, we can break it down and we can make a group of just numbers that we use to count naturally. Now there might be other numbers that we use when we count sometimes, but typically, if I were to say count to 10, you would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my example of counting or natural numbers is going to be 1, 2, 3, and so on. My lowest counting number is 1. All right, this group is not going to include any negatives, and it's not going to include 0, and it's not going to include any fractions or decimals. It is only these positive whole numbers. All right, so that is my smallest set. Next, I have whole numbers. So whole numbers are going to be the set of all those natural counting numbers, so all the positive whole numbers, plus 0. So all we're doing here is we're adding one number. So for example, my numbers are going to be 0, 1, 2, 3, and so on. All right, so I had my counting natural numbers. That's my smallest group. It is all the positive whole numbers. And then my next set, which is slightly bigger, is the whole numbers. So it's all of those counting natural numbers plus 0. Now I have integers. So the integers are going to be the set of all the whole numbers plus their opposites. Plus their opposites, which is the same as saying their negatives. So this still does not include any decimals or fractions. We're still talking about those whole numbers. So now I'm going to have my typical 0, 1, 2, 3, and so on. But I'm also going to have their opposites or their negatives. So I'm going to have -1, -2, and so on in that negative direction also. So now I have my positives and negatives, and then 0 is also an integer. All right, so I had my counting natural numbers. That's my smallest group. And then my whole numbers, all I'm doing is I'm taking those counting natural numbers and I'm adding 0 to it. And then integers, all I'm taking is those counting natural numbers plus 0 plus the negatives. And now I have rational numbers. So rational numbers are the set of numbers that can be written as fractions. These can be written as a fraction. So this is all of those integers, which includes whole numbers and counting natural numbers. And then this includes fractions, obviously. It also includes decimals that either terminate, so they end, or they repeat. So if I were to write some examples in here, I'd have a random natural number. I have 0, that's my whole number. I have a negative number. I have a fraction. I have a decimal that ends. So that means at some point it ends. There's no more numbers after this 2. I have a decimal that repeats. So that means it has that line on top of it. That means it repeats in that same pattern over and over and over again. What it does not include is a number like this. So that ... or that ellipse at the end of that means that those decimals are going to go on forever, but there's no pattern to it. And that is going to be irrational numbers. So irrational numbers are any numbers that cannot be written as a fraction, or any numbers that are not rational numbers. If we think about what irrational means, the prefix ir means not, and then I have rational, so not rational. So these are just numbers that cannot be written as a fraction. So my example that I had just had up here was something like 0.346 ... There's no pattern, there's no end to that decimal. And so all of these are real numbers. And real numbers are the set of rational and irrational numbers. So within this real number system, every single number is either going to be rational or irrational. It can either be written as a fraction or not as a fraction. There's no other options. One thing I want to point out before we move on to the back side of this note guide is for rational and irrational numbers, I can also look at these numbers as square roots. So I need to know the difference between different square roots. So when I say square roots, I mean numbers that are under a sign like this. So in order to know that, I need to know this number right in here. So that number is called a perfect square, and I get that by multiplying a number by itself. So I'm going to list off the first couple perfect squares, and then on your own you can continue on listing the rest of them. So I'm going to start by multiplying 1 by itself. So 1 times 1 is 1, and then 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and then that can go on. So these numbers here are my perfect squares. 1, 4, 9, 16, and then so on. So if I had square root of 4, I need to look at this and think, is the number under that square root sign in this list? If it is, then it is a rational number. But if it's not, so say I have square root of 17, it's not in that list, so that would make it irrational. The other thing I need to think about is if I have a number that simplifies. So if I have 4 over 2, for example, that simplifies to 2 over 1, which is the same as 2. That number is actually a counting natural number. So you need to make sure you're looking at simplified versions of numbers when we are figuring out what subset these numbers belong to, which is what we're doing on the back side of this. All right, so let's go ahead and flip this paper over, and we're going to look at a different way to visualize this real number system. So here in this box, I have all my possible real numbers. So this is my real number system in here. And so I'm going to start with that smallest number again. So I started with those counting natural numbers. That's my smallest group, and that's going to be right in here. So all of those positive whole numbers would fit inside of this circle right here. Next, after my counting natural numbers, I had my whole numbers. So the only thing that I add to that is 0. So notice that the counting natural numbers circle is completely inside of the whole number circle. So that means that any counting natural number is within that whole number group. So if it is a counting natural number, then it is always going to be a whole number. All right, next after whole number, I have integers. So notice that the whole numbers and the counting natural numbers are completely inside of the integers. And then after integers, I have the rational numbers. So every single integer, every single whole number, every single counting natural number is within the rational numbers. So if it is any of those, it is also rational. And then over here on the side, separated from all of those are the irrational numbers. So if I have a number that's irrational, then there's no way it can be any of those numbers over there. All right, so how exactly are we going to use this all? Let's go ahead and go through some examples. So you're going to have problems like these. So yeah, you're going to be given a number and you have to state every single subset that the number belongs to. So let's start with -8. So -8, I'm going to start on the outside and work my way in. I'm going to think to myself, is -8 rational or irrational? Well, -8 is rational because it's not a decimal that goes on forever. So I'm going to move in one circle. Is -8 an integer? Yes, it is, because it is the opposite. It's the negative of a whole number. So next I'm going to see if it's the next circle in. So is -8 a whole number? Well, remember, whole numbers are only 0 and then those positives. So it is not a whole number, which means it's also not going to be a counting natural number. I can stop at whole. And so I need to list all of these. And remember that it is also a real number, and we need to list that as well. So -8 is an integer. It's rational. And it is also real. All right, let's do the next one. -5,621.1001235.3 ... This ... tells me that it is irrational. And remember, if it's irrational, then it's not going to be anything else except real. Every single number that we work with is going to be a real number. All right, this next one, 1.333 ... Well, this ... tells me that it's going to go on forever, but it has this pattern of 3s. So another way this could be written is 1.3 repeating. So remember that repeating numbers are rational. And since it's rational, I have to see if it's anything else. So is 1.3 repeating an integer? No, it's not, because it is a decimal, and decimals are not integers. So this is just rational and real. Go ahead and do the next one on your own and see if you can figure it out. Once you get it, we'll pause the video to do it. Once you get it, play the video and see if your answer agrees with mine. So the next number I have is 61. So first I'm going to think to myself, is 61 rational or irrational? Well, it's rational because it's not a never-ending decimal. And so now I have to ask, is it an integer? Well, it's a positive whole number, which means that yes, it is an integer. And I just said that would make it's a whole number. And it's a positive whole number, which means it is a counting natural number. So this is rational, an integer, a whole number, a counting or natural number, and then it is also real. All right, let's go ahead and move on to 49%. Now, I will tell you that if you are not very familiar with percents can be converted to decimals and fractions. So 49%, if that can be written as a fraction, then it's going to be rational. And then we should know that if it is a fraction, then it is not going to be an integer. So this is just rational and real. Next, I have 11 over 10. Well, 11 over 10 is a fraction, so just like I said, that is going to be rational. And that does not simplify to an integer, so it's just rational and real. All right, now we're getting to these square roots that I was talking about a little bit on the front page. So let me remind you that I can write out my perfect squares. And you should go ahead and do this in this space on yours also. All I'm doing is I'm going one by one. I'm multiplying each number by itself, and I'm listing out what that product is, so what they multiply to. And then I'm going to go ahead and stop at 10, even though this could go on forever. So all of these numbers here, all the products of this multiplication are my perfect squares. So when I get the square root, like this problem right here, I need to think to myself, is the number under that square root sign in this highlighted list? Well, 16 is, so square root of 16 is actually saying 4. So the square root of 16 is the same as 4, so if I'm looking at the number 4, and I'm figuring out where that lands, I know that 4 is rational. 4 is an integer because it's not a decimal or a fraction. It's whole and counting or natural because it's positive. And then, of course, it is also a real number. All right, next I have square root of 2. So I have to look at this number under the square root, which is 2, and I have to think to myself, is 2 in that highlighted list? No, it's not, so that automatically tells me that this is going to be irrational. And then it is still a real number, even though it's irrational. One thing I want to point out real fast is some people sometimes mix up rational and irrational with positive and negative. Positive and negative have nothing to do with rational numbers versus irrational numbers. Decimals are what make numbers rational and irrational. So we have to look at that decimal. It has to be able to be written as a fraction. My last number here is pi, which we should know is 3.14 something something something. That goes on forever. That decimal goes on forever. There's no pattern to it, so that means it is irrational. And then, of course, that is still real. All right, we're going to go ahead and go on to the last example in these notes. So we have a set of numbers because it is written in these curly brackets, and we have to place them in the correct spots on this Venn diagram. So real quick, a reminder on Venn diagrams. I have two circles here. This first circle is the integers. So any number that's an integer is going to land somewhere within that red circle. My other circle is the whole numbers. So if we have a whole number, it's going to land somewhere within that blue circle. So if we have numbers that are integers and whole numbers, we're going to put it here in this overlapping spot. If we have numbers that are only integers and not whole numbers, it's going to land in that red spot. And then if we have numbers that are whole numbers but not integers, it's going to land in the blue spot. All right, so let's go ahead and try these out. We'll do it one at a time. So my first number is negative 0.462. So I have to think to myself, is that an integer? No, it's not, so it's not going to be in that circle. Is it a whole number? It's also not a whole number, so it's not going to land in there. If it doesn't land in any of the circles, then that means it's going to be somewhere out here where it's a real number but not an integer or whole number. So I'm going to go ahead and put it right here in this spot. All right, my next number is negative 56. So I have to think to myself, is that an integer? Well, it is a negative whole number, so yes, that is going to be an integer. Is it a whole number? Well, it's not 0 and it's not positive, so no, it's not a whole number. So I know that negative 56 is going to land right here. Next, I have 735. Once again, I'm going to ask myself, is it an integer? Yes, it is, because it does not have a decimal. And then I have to ask myself, is it a whole number? Yes, it is also a whole number because it is positive and it does not have a decimal. So it will go in the middle where the two circles overlap. I have just a couple more. Go ahead and do these last ones on your own. Pause the video, work them out, and then play the video and see if these land in the correct spots. My next number is 0.326. That is a decimal, which tells me it's not going to be an integer or whole number. So I'm going to write it right out here. Next, I have 8,321. Well, that is positive. It's a whole number. So that tells me it's going to be an integer and a whole number. So I'm going to write it where these two circles overlap. And then my last one is 0. Well, I know 0 is that special whole number. And then it's also going to be an integer. So once again, it's going to be where the two circles overlap. One thing I want to point out real fast is no numbers landed right here in this spot. So take just a moment and think through why you think no numbers landed there. If we look back to our diagram of the real number system, notice that our whole numbers, that circle is completely inside of the integer circle. So any number that is a whole number is also going to be an integer. There's not a single number that's a whole number and not an integer, which is why no numbers landed in that position. You should be able to finish up your homework from this section now, so make sure you get that finished. And then the answer key is on Canvas for you to grade on your own. And then, of course, make sure you fill out that homework completion log. If you still have any other questions about this section, go ahead and come in and talk to me outside of class.